Thanks for staying. I'm here to talk about a NoSQL data store which powers Prime Day sales and a lot of properties at Amazon, DynamoDB. DynamoDB is a lot of learnings from us operating and building NoSQL data stores like Dynamo and Amazon SimpleDB, and a lot of what customers liked and did not like about these NoSQL data stores. Right? Dynamo is a fully managed NoSQL data store. What I mean by fully managed is, unlike traditional databases, you're not provisioning servers. All this is hidden behind. All applications do is just create tables with the key schema and then can drive workload. They do not have to worry about patching, downtime. All this is taken care under the scenes, under the covers by Dynamo. It automatically recovers from all failures as well. We are a multi-tenant data store, which means that data of different customers are co-located together because we have a vast amount of resources and we want to be able to efficiently use these resources. But at the same time, we also want to make sure that there is good workload and security isolation between one customer's data from another customer's data. The schema is very flexible. It's just a key value store. You need to know what the schema for the key is, and the value can be any arbitrary attributes and values in a document. One of the key things about Dynamo is that it's got very simple APIs, simple put, get, delete, and update, and query and scans. This allows also us to have a very predictable performance no matter what the throughput of the workload is and the scale of the table is. So your table might just have 4 items, or it might have like 4 million items, but you can expect these simple APIs to be very predictable and have single-digit millisecond latencies. Dynamo is a very highly available service. We have an external SLA of 4 nines for regional tables and 5 nines for global tables. We replicate data across 3 availability zones. An availability zone is a group of data centers which have redundant network and redundant power, so to isolate each other from like power outages and other natural disasters. Last but not least, it's boundless scale, so you don't have to worry about how much throughput your workload needs and what's the scale of storage you need. We're going to elastically scale. Just to give you an idea of the stats, these are the stats from the previous 3 Prime days. And this is the peak RPS we handled on each one of these Prime days. And I'm sure that we're doing a lot right now as well. And this is just the peak RPS of just the Prime Day traffic. We have a lot of other customers, a lot of other regular traffic on top of this, which we handle with single-digit millisecond latencies and high availability, because any one of them having higher latency would kind of impact all downstream consumers of this. Over the years, as I said, Dynamo was the inspiration to build NoSQL data stores. DynamoDB just started as a simple key value store, and then we've been adding features on top of this as and when we've been hearing back from customers what they wanted. Right? One of the key things I get asked, and every time I go everywhere, is that, hey, what's the difference between Dynamo and DynamoDB? This is something I got asked in the booth as well. There are a lot of differences. Dynamo is single tenant, DynamoDB is multi-tenant. Dynamo had a different consistency model versus DynamoDB. Likewise, Dynamo preferred availability over consistency. Dynamo prefers consistency over availability. But one of the key differences is the routing and storage were coupled in Dynamo. Dynamo used consistent hashing to decide where the data was stored. But like I'm going to present and talk about it and some more slides later, DynamoDB actually has decoupled routing and storage. Now, I want to set up some background and architecture on how Dynamo works so that we can kind of talk about the lessons we've kind of learned in operating the service. So I'm going to work through this architecture using a simple put item as an example. So when when an application issues a put item call, it traverses the network and then reaches from a load balancer to the request router. So request router has got a specific set of duties. One is first authenticate the call, make sure it's the right person, right application, right person calling the thing using AWS Identity and Access Management Service. And then it looks up metadata to figure out, okay, where to find the key, what table does this request belong to, etc. And then kind of does some admission control decisions, and then forwards it to the right storage node, which can actually serve this request. And that storage node is then responsible for accepting the request and replicating it across its peers on different availability zones. Why do we need to do all this? We are not a single request router, single storage node. There's thousands and thousands of request routers and thousands of storage nodes. So we need to locate this data. And any one of these request routers can actually get this data and these components across different availability zones, as I mentioned before. So the request routers plus metadata actually provides us the decoupling we need from the storage. So request routers are responsible for routing the data to storage, and the clients don't have to worry about, hey, where does my data go? Once the request router finds out the nodes hosting the data, it sends out, in this case, it's a put item request, so it has to be routed to a leader. It routes it to the leader, and the leader is then responsible for replicating the data changed to its peers. And once a quorum of peers accepts the change, you acknowledge back to the customer saying, hey, yes, you're right, it's durable. The leader is leader election. For leader election, we use a version of Paxos, multi-Paxos. And leader periodically heartbeats to its peers. If the peers detect that the leader has failed, a new leader gets elected very quickly. Now, DynamoDB scales partitions, tables by partitioning them. So I'm going to work through an example here. This is a very simple example of a customer information table where the unique key identifying the row is going to be the customer ID, which is the GUID. And then the customer information has various attributes like name, address, zip code, a bunch of these things, right? Now, how is Dynamo going to partition this table? So Dynamo basically under the scene takes the customer ID, which is unique, and the customer specified, hey, this is going to be my key, which uniquely identifies the row, and then runs it through a one-way hash. And this hash allows us to randomly distribute the data across different across the table. And once it's hashed, then we decide, okay, fine, we will kind of divide the table based on these hashes, right? We've now divided this table into 3 different partitions based on the hashes. The first partition gets keys from 0x00 to 0x6ff, and the second partition gets data from 0x7 to B, 0xB, and the third one gets 0xC to 0xF. So now this kind of allows this partitioning. How do we decide how many partitions do we create? That depends on what the throughput requirements of the table is, what the size of the table is, right? Now the data from these partitions is replicated 3 ways, so they can be stored in they're going to be stored in different storage nodes. Each one of the storage nodes, as I said, is multi-tenant, so replicas partition data from other multiple tables can be located along with the stuff. For example, the green partition is stored on the green storage nodes, the orange on the orange storage nodes across this one, and the pink on the pink storage nodes. And all this data is stored in something called as a partition map, whose key value is a key, which is keyed by the table name and the partition ID. And the partition map contains information like, okay, this is a key range, and these are nodes which are storing this data, right? And this allows the request router to find out, okay, where is this particular key, which storage node to route to this particular key to. I briefly mentioned about how the partitioning of the table is determined. Now, in this section, we'll go over one of the lessons we learned over operating the system over a period of time, which is basically that we had to adapt to customers' traffic to actually kind of decide the physical partitioning scheme or how we implemented admission control, right? So why is admission control necessary? It's slightly unique to Dynamo because Dynamo is one of the systems where you don't provision instances, but you actually kind of use to provision tables using read capacity units and write capacity units. So one read capacity unit would allow you to read up to a 4 kilobyte item with strongly consistent read, and one write capacity unit would allow you to write an item of up to 1 kilobyte. Now, this is very different from most other systems. So when when we partition a table, what we did is that we took this read and write capacity units and distributed it evenly across all the partitions. In this example, I'm going to just use the read capacity units, skip the write capacity units. This table was provisioned, let's say this table was provisioned with 300 read capacity units, then each one of these partitions would get 100 read capacity units. Now we had to implement workload isolation. Simplest way to do this workload isolation is a token bucket, right? Like you have 100, the token bucket has 100 read capacity units, which is filled at a rate of 100 RCUs. This works great because if there's a token in the token bucket, the request is admitted, and if the token is not there, it's great. The request is rejected, and there's good workload isolation completely for across multiple partitions. But what we found in practice was that it's really hard for customers to actually get uniform distribution of request rate across time, right? So most of the time, the partitions would be serving more than less than 100 write capacity units, and then there would be a spike of traffic which is greater than 100 read capacity units. What happens then? The customer gets throttled, and this was kind of a very bad experience overall, and they would have to retry this request, incurring high latency. So how did customers work around this stuff? They kind of over-provisioned the table, right? By over-provisioning the table, the partition would have more capacity, which basically meant that they had to plan for their peak capacity at this point in time to decide what would not get them, have them throttled. So most of the time, a lot of the capacity was wasted. This was very inefficient for us and inefficient for the customers. So what did we do? A simple thing, right? Like back in the day, I don't know, about like 5-6 years ago, cellular plans have this rollover minutes. You could roll over your minutes up to a particular max limit. A very similar thing, we allowed bursting. So we increased the capacity of the bucket to a max of 3,000 read capacity units, or whatever is 5 minutes worth of read capacity units allocated for the table. And said, okay, if you're not using a capacity for up to 5 minutes, we're going to accumulate that. You can accumulate that capacity and later use it. What this allowed customers to do is to have spiky burst traffic. But this also meant that we had to make sure that at the node level you had capacity so that you don't interfere with other workloads overall, right? Now, the other thing which customers found really hard was uniform distribution over keys. Let's say that I'm running a census app. And the data in the table is partitioned by postal codes or zip codes of Canada, right? From this map, you can see that there's going to be a very few set of postal codes or zip codes which are going to get really high traffic versus the ones above the red line. So those partitions would get throttled because they're constantly running out of tokens from their bucket, even though they had burst capacity, because after the burst capacity is over, you have to still take time to fill capacity in the token bucket, while other partitions actually had capacity in their token buckets. So a key takeaway from this was, though bursting was great, it solved some of the customers' problems, it wasn't sufficient enough, and we had tightly coupled how partition level capacity to admission control, right? So we realized that removing the admission control from a partition level would be the most beneficial thing for customers and for us as well, and letting the partition burst always. So we implemented something called as the global admission control, where we moved admission control up front. Now, GAC is a service that builds on the same token bucket mechanism. So when a request router receives a request, it basically requests GAC to kind of get some tokens. And once request router uses the local tokens to make admission control decisions. If it runs out of tokens, it can actually request for more tokens. If there's no capacity, GAC is then not going to give the request router tokens, and request will be rejected. This helped a lot of customers because now customers are able to burst across their partitions constantly and have less throttling. This also meant that we had to have very smart placement algorithms of these partitions and replicas across our entire fleet of thousands of storage nodes, because to be able to burst a partition to burst always, we needed to have capacity at the node level. So a lot of the work went into how do we smartly place these partitions and replicas across this entire fleet of storage nodes so that we can have partitions burst always. Now I want to switch gears, since I have very little time. I'm going to talk about another lesson we learned where we said, we need to build systems for predictability over absolute efficiency so that we can improve the system stability. How did we learn this? Back in 2015, 3 years into the service, we had a very large event. It was quite a bad day, not only for Dynamo, but for Dynamo's customers as well, because they couldn't reach us, right? Why did we have this outage? So we talked about how a put item request works, the request order request for the partition metadata. It actually gets a partition map, and this was because the partition metadata was keyed off a table name and a partition ID, so it had to get the entire list of partitions for the table to look up where the key is located. This worked great in a regular way because a request order would request this information, it would get cached locally, and then the request order could reuse this information all the time. In 2015, this information slowly grew. We were growing really big, and caches were actually hiding the fact that this data had kind of grown big for every table in Dynamo, right? And when a lot of request orders, a lot of clients for this data, just not request orders, but other components in Dynamo, but started requesting this data, the partition metadata system could not handle this. So we were kind of in a state of a metastable failure, which was one of the talks before where they talked about metastable failures in the wild. And the partition metadata system we couldn't even scale out the partition metadata system to actually kind of recover from this scenario, right? Why did this happen? Because the caches actually hid the fact that our partition map cache was growing. We had a 99.75% of hit rate, so caches were lovely. But all of a sudden, when the cache hit ratio was the cache hit ratio was 0, all this traffic went to partition metadata. So from a miss ratio of 0.25%, we went to a miss ratio of 100%, which is a 400x spike in traffic rate. So to recover from this, we literally had to kind of turn off querying metadata for a long time, which meant that we couldn't kind of serve requests, and then scale out the partition metadata system to remediate the system, to remediate the event. But we wanted to think long term, right? So we built something called as memory data store, which is a distributed in-memory cache. There are two key properties to this. One is that we realized we didn't need the entire partition map cache to serve a request. Right? We just needed that one single piece of data of which three storage nodes are hosting this data. So memds is, we changed the data structure we're using. We uses a Perkle, which is a hybrid of a Patricia tree and a Merkle. It supports queries such as floor and ceiling, which basically takes a key and says, okay, give me the floor value of this particular thing, which actually leads us to find the right partition hosting that particular key. It also, so now with memds, we could send this request. We can scale out horizontally. Like we have a lot of memds nodes, we scale out horizontally. We get the single data we want, right? But even though memds, we cache this data locally in request order, still, we actually keep sending requests back to memds asynchronously for every request, even if we get a cache hit. The reason we do this is that we want the system to actually do constant work all the time, right? We don't want a system to have a sudden spike in traffic and not be able to deal with that stuff. So memds is constantly, we're doing constant work across memds. So for every request Dynamo gets, memds gets the same amount of requests. I would like to conclude by talking about the 4 lessons we've learned and we kind of talked about in the paper. I talked about the first 2. The other 2 I've not kind of talked about, and you can kind of refer to the paper, is that continuous verification of data is super important. We learned this over operating the system in 10 years. There are hardware bugs, software bugs, so we need to be able to continuously verify and detect any corruption to data at rest. The other thing is that as Dynamo grows, there are a lot of services which are needed to support a lot of features I talked about. And this requires careful operational tooling and discipline, right? So we use a lot of different things we talked about earlier in the conference, such as formal methods, fuzz testing, upgrade, downgrade testing, chaos testing. So there's a lot of work which goes behind the scenes to get every feature released and also make sure that we do not lose our correctness properties of the system. With that, I would like to conclude my talk. Thanks for staying for the last 20 minutes. I know this is the last presentation of the last talk, last session. If you want to chat more, here's my email address and my Twitter handle. Please feel free to send me an email.